Welcome, everyone. My name is Peter Corliss, Technical Marketing Manager at ScyllaDB. I'll be your moderator for today's webinar, comparing Apache Cassandra 4.0, 3.11, and Scylla Open Source. Many of you know about Apache Cassandra, one of the most scalable open source NoSQL databases available. Scylla is a big, fast NoSQL distributed database, perfect for highly available, highly performant terabyte scale workloads. It was patterned after Cassandra and also offers a DynamoDB compatible API. But without any further ado, I have the pleasure of introducing to you our speakers today, Piotr Grabowski and Karol Barewa, the software engineers at ScyllaDB. Take it away, Piotr and Karol.
Thank you, Peter. So my name is Piotr Grabowski. I'm a software engineer working here at ScyllaDB. For the past year, I have worked on mostly Java projects here at ScyllaDB, so our Kafka connectors and also the Scylla Java driver. Today, Karol Barewa will be presenting together with me. Karol, could you say a few words about yourself?
Hello, I am Karol. I am a junior software engineer at ScyllaDB since July this year. And I work here on C++ and Java drivers and also on CDC connectors and library.
Thank you, Karol. So let's get going. So today's agenda will be as follows. First of all, we'll cover our testing methodology. So how we started benchmarking Cassandra 3, Cassandra 4, and Scylla, what type of tests we chose, what types of instances we used, how we configured both databases. Next, we'll get into a comparison between Cassandra 3 and Cassandra 4. As you will see, there's a big difference between the performance of Cassandra 4, especially the latency numbers. Next, we'll go into comparison with Scylla. So is Scylla still a better option compared to Cassandra, even with all the improvements of Cassandra 4? And finally, we'll have some portion of conclusions. So if you are wondering if you should switch to Scylla or maybe consider Cassandra 4, that's the part we will cover those decisions in. So a few words about ScyllaDB. I saw that many of you use Apache Cassandra, so you might not be so familiar with our company. Here at ScyllaDB, we develop a real-time big data database, Scylla. It's, of course, a drop-in replacement for Apache Cassandra. And we also have introduced compatibility with Amazon DynamoDB API as our project alternator. We offer outstanding performance and low tail latencies, as you will see later in this webinar. We have the ScyllaDB database is available as an open source software, but we also offer an enterprise support with additional features such as advanced encryption methods and enterprise support. And we also offer cloud, Scylla Cloud, which allows you to manage your database without much worry and without spending a lot of time managing it. Our company was founded by Avi Kiviti, amongst others, which was a creator of KVM hypervisor. So we have a very strong technical foundation at our company, and we have many people working around the world, in USA, in Israel, and in Poland. I'm from Poland. So this year, a few months ago, Cassandra has released version 4.0 as final general availability of this version. This version came 6 years after the release of version 3. So a lot of things have changed in those 6 years. So let's see how Cassandra has improved and how well it holds against Scylla now. So first, let's cover some new features that were introduced in Cassandra 4. First of all, Cassandra 4 has increased speed and scalability. So 2 points that prove that claim. First, Cassandra 4 has introduced zero-copy streaming, which allows you to stream data between nodes. So for example, when a node is added, the data is streamed to this node, and zero-copy streaming allows you to potentially copy the data at the speed that is only reduced by your throughput of network, not by CPU. So you could potentially achieve gigabyte per second copies streaming of the data. But as you will see, it's not all roses in that aspect. Cassandra 4 has also faster throughput by about 25%. That's the official number that Cassandra folks have presented, but our measurement have confirmed this number. The second point is that Cassandra 4 has introduced support for newer JDK versions, so JDK 11. And with newer versions of JDK, there comes new garbage collector algorithms, which, as you will see, is a great improvement for the latency numbers. Of course, there's some new configuration settings, better security settings, and observability. They have introduced new compression settings, new compression algorithms. And the final point that Cassandra 4 was released after 6 years of development of Cassandra 3.0. So now the developers have shifted into a 12-month release cycle. So we'll see how well it goes, but it will mean better releases of Cassandra more often. And comparing the release schedule of Cassandra and release schedule of Scylla, as you can see, Scylla has introduced new versions of its database much more often, essentially every year, while there was a big gap in Cassandra 3 between Cassandra 3 and Cassandra 4. So now let's go into the methodology section. So Karol, could you tell us more about it?
So yeah, before we present the results, we need to talk about what did we measure and how did we measure it. There are two major parts to our benchmarks. The first one is a traditional latency and throughput comparison. In this part, we measured a few different workloads so that we could get a better idea about performance characteristics of both databases in different use cases. As you can see, there are 3 workloads that we have tested. The first one is a Gaussian distribution workload. And this is something you could call a real-world workload. It means that the big portion of the traffic goes to the small part of the rows, while the rest goes to the rest of the table. That way, the cache is utilized a lot, but the disk is still, the disk is still not used, it's not sleeping. The cache hit, if I remember correctly, was about 30% in this test for Scylla. So the workload touches both the cache and the disk. In the disk-intensive workload, each row in the table had an equal chance of being used in a query. Each row is equally likely to be used in a query. In such workload, the cache hit is extremely low. If I remember correctly, it was about 3% for Scylla. So nearly all operations require some reads or writes to the hard disk. And the third workload is the memory-intensive workload, And this is the complete opposite of disk-intensive workload. Here, pretty much whole traffic goes into the small portion of the table. Small enough that it can fit in the memory. So the cache hit ratio is very close to the 100%. Hard disk isn't really used. In each of those three workloads, we tested three scenarios. Write only, so all the operations were writes. Read only, all the operations were reads, selects. And also a mixed read-write. So 50% of the operations were reads and 50% were writes. Now, the second major part, that to be honest is benchmarked and talked about much less often, is the administrative operations part. We benchmarked a few types of those administrative operations. First of all, adding a new node to the cluster, adding a single new node, or even doubling a cluster size. Apart from that, we benchmarked replacing the nodes, so which happens if one of your nodes breaks and you need to replace it. We also benchmarked major compaction time. But why are we even measuring these things? Raw throughput and latency is not everything. In real life, you also need to manage your database. You need to add new nodes to scale up to adapt to traffic. When node breaks, you need to replace it. And the speed of those operations directly correlates with the ease of usage of the database. And I think it may also correlate with the lower costs. For example, if you can scale up to the traffic faster, then you don't need to over provision so much, and perhaps you can. Oh, sorry, I lost the word. Yeah, but it may be less expensive in the long run. Can you go to the next slide? Okay, no, this slide. So all the benchmarks were run on AWS in the US is2 availability zone. For the free versus free benchmarks, so the benchmark when Scylla runs on free nodes and Cassandra also runs on free nodes, we used a total of 6 nodes. 3 were for cluster, and those were E3.4x large. And each of those has 16 cores, vCPUs, 122 gigabytes of RAM, and 10 gigabit network. We also used loader nodes. Those were the nodes where the clients, the benchmarks itself, were running. And for those nodes, we used C5M.9x large, each holding 36 vCPUs and 96 gigabytes of RAM, and a really fast network up to 50 gigabits. For the second part, the 4 versus 40 benchmark, so the benchmark where Scylla is running on 4 nodes and Cassandra on 40, Scylla was running on 4 E3.metal nodes, each having 72 vCPUs and a half terabyte of RAM. And Cassandra was running on the same nodes as in the 3 versus 3 benchmark, so E3.4x large nodes, but this time there are 40 of them, each having 16 vCPUs and 122 gigabytes of RAM. In each benchmark, Cassandra 4 was running on using JDK 16, and Cassandra 3 was running using JDK 8.
Thank you, Carol. So now we'll get into the results section. First, looking at Cassandra 3 versus Cassandra 4. So we'll see how Cassandra 4 has improved over the years of Cassandra 3. So first of all, let's start with the latency numbers. So let's start with a Gaussian distribution. So as you can remember, this is a distribution that a large portion of the load is directed at a small portion of the data set. However, there's still some load to the remaining parts of the data set using the Gaussian distribution as the mechanism to achieve that. So this graph shows the write latencies in the mixed workload type of this benchmark. So first of all, it will be similar between the graphs. When a graph ends at some point, so for example, the yellow lines signify the Cassandra 3 results of their latencies. So when a graph ends at a certain point, so for example, 30,000 operations per second, it means that the database couldn't handle the next step. We measured the latency at different throughputs, but of course we had to choose certain points at that we measured the latency numbers. So when a line ends at some point, that means that the database couldn't handle the larger load. It would not achieve this throughput, or maybe the latencies would be very high, above 1 second. So looking at those results, as you can see, the Cassandra 3 latencies are worse than Cassandra 4, especially if we look at the 99 percentile latencies. So those are the lines that are a bit thinner. As you can see, the 99 percentile latencies of Cassandra 3 hover around 500 milliseconds, so 1/2 of a second, which is not a great number to achieve. And even the 90 percentile latencies are getting above 100 milliseconds. But if you look at the Cassandra 4 numbers, for a great portion of this graph, they are below 10 milliseconds. So one thing to mention, this graph is in logarithmic scale. So that's because if we wanted to show it in linear scale, you wouldn't see the Cassandra 4 numbers. They are so much better than Cassandra 3. So the last slide showed the Gaussian distribution write latencies in the mixed workload. This graph shows the read latencies. So they are a bit higher, but the trend is the same. Cassandra 4 wins, and the Cassandra 3 latency numbers, especially 99 percentile latencies, are so much worse than Cassandra 4. So now we'll move to disk intensive workload. So first of all, as you can see, Cassandra 3 lines end a bit sooner than Cassandra 4. Cassandra 3 ends its maximal throughput at 40,000 operations per second, while Cassandra 4 can achieve up to 50,000 operations per second. So there's the 25% improvement in maximal throughput that the Cassandra developers have advertised, and in our measurement, it holds true. And as you can see, the 99 percentile latencies are essentially above 100 milliseconds for Cassandra 3. But if we look at Cassandra 4, especially the first part of this graph, maybe not the maximal throughputs, the latency, even the 99 percentile latencies are well below 5 milliseconds. If we look at the read-only latencies, when most of the requests have to go to the disk, so the disk-intensive workload, as you can see, the 90 percentile latencies of Cassandra are below 10 milliseconds. Cassandra 3 could also achieve this result, but it only could achieve 30,000 operations per second, not 40,000 operations per second. And moreover, the 99th percentile latencies are improved. So for example, at 20,000 operations per second, the latency is between 5 and 10 milliseconds, the 99th percentile latency, while Cassandra 3, 99th percentile latency is well above 10 milliseconds. When we look at memory intensive results, so in this example, in this measurement, we gathered it's 100% writes. The memory intensive workload, Cassandra can achieve up to 40,000 operations per second. And the latencies of Cassandra 4 are much better. The 99th percentile latency is above 10 milliseconds for the entire benchmark, while Cassandra 3's 99th percentile latencies hover around 500 milliseconds. They are well above 100 milliseconds. If we look at the read-only benchmarks, essentially the same pattern holds true, although latencies are a bit higher. So we have covered the latency throughput benchmarks. So now let's go into administrative operations. So maybe those types of benchmarks are not performed as often as the latency numbers, but administrative operations are also crucial to keeping the cluster healthy, especially if there's a downtime or there might be a peak traffic. It's crucial that those operations are rock steady and very performant. So in this timeline view, I have shown the time it takes to add 3 nodes to the cluster. And as you can see, adding nodes to Cassandra 4 was faster. So in case of Cassandra 3, it took over 4 hours. But in case of Cassandra 4, it was below 4 hours. And as you can see, it was a pretty sizable test. Each node that was added had to stream more than 400 gigabytes of data from other nodes. So if we focus on the operation of adding a single node, those are the numbers that we measured the time it took to add a new node. We tested 2 scenarios, 2 compaction strategies, STCS and LCS. The reason we wanted to also test LCS strategy is because this strategy produces SS tables that might be better suited for the 0-copy streaming. In Cassandra 4, when there's a 0-copy streaming operation, when a node discovers that the entire SS table can be streamed to another node, so it doesn't have to trim this SS table or read it row by row, it can just copy the entire SS table essentially at the full network speed. So as you can see from these graphs, we can see a big improvement when it comes to LCS variant of this test. The improvement in time is much bigger than in STCS workload. However, in both tests, Cassandra has improved in version 4 when it comes to adding a new node operation. So when it comes to doubling cluster size, those proportions are essentially the same. But as you can see from this graph, when you use LCS strategy, you can save 1 hour of administrative looking after the cluster, waiting for it to add a new node, adding many new nodes. You can get it done in less time. You can save 1 hour in this case. Another operation that is crucial is replacing a node. So for example, if one node in your cluster dies or there's some hardware issue, you might want to deprovision this node and launch another node, and this node would replace the old node. Of course, it must stream data from other nodes, and this is the benchmark we performed. We stopped one node and launched another node, which replaced the old node, and we measured the time it took to bootstrap this node. And as you can see, replacing a node, there's a big improvement in Cassandra 4, especially with LCS strategy. So maybe a bit summing up the results. What caused the latency of Cassandra 4 to be so much better? So the quick answer is that the JDK has improved so much compared to Cassandra 3. So Cassandra 3 only supported Java 8 officially. However, Cassandra 4 officially supports Java 8 and Java 11. Java 11 has introduced a new compaction algorithm, ZGC. First, it was an experimental feature, but now in Java 15 and later versions of Java, it's production ready. ZGC promises extremely short pauses, so pauses that can be less than 10 milliseconds, while other garbage collection algorithms in Java 8 could take hundreds of seconds. And when a garbage collection process kicks in while a request is processed, this can mean that the request is delayed in sending a response to a client. And in our benchmarks, we use Java 16. Even though Java 16 is not officially supported in Cassandra 4, we wanted to give the best possible environment for Cassandra to achieve the best results it could have achieved.
All right, thank you, Piotr. Hello again, everyone. Peter here. I just want to take a moment for a quick audience poll. Just for a sense of scale, we'd like to understand how much data do you have under management in your own transactional database systems? Less than a terabyte, 1 to 50 terabytes, 50 to 100 terabytes, or greater than 100 terabytes? Pick the answer that best matches your current data set. Thank you. We'll leave the poll up for a bit for you to answer. Also, remember to use the Q&A feature to ask your questions at any time. We'll answer them all at the end. Now, let's get back to the presentation.
So now we'll get to the Scylla versus Cassandra 4 and Cassandra 3. And Carol, let's get going.
Okay, thank you. So now we have seen that Cassandra has improved in the last 6 years. It has improved quite a lot. Although the big portion of those improvements, as we have seen, come from the new Java versions and new garbage collectors. But there are also some nice throughput and administrative operations improvements. So the big question now is it enough to catch up to Scylla in terms of performance, or is the gap still too big? So let's go over the same tests as before, but this time with the Scylla results included in the graphs. So here we have again the Gaussian distribution with the 50-50 workload, and those are the results for write operations. So as we have seen previously, Cassandra 4 increased its max throughput from 30 to 40,000 operations per second, but it is still nowhere near Scylla, which can reach as high as 80,000 operations per second, and that is about twice what the Cassandra 4 can achieve. Apart from that, when handling 40,000 operations per second, Cassandra 4 P99 latency approaches about 500 milliseconds, which is quite a lot. And P90 latency exceeds 50 milliseconds. At the same time, Scylla's P99 remain under 10 milliseconds, and P90 remains under 5 milliseconds, all the way up to 80,000 operations per second. Yeah, can I get the next slide? Okay, here the situation is pretty much the same as on the previous slide. The read and write latencies are very similar. The read latencies, I think, are just a little bit lower, but all the proportions are still the same as before. So there is, not much more to talk about here. Let's move over to the disk intensive benchmarks. So here the throughput difference between Scylla and Cassandra becomes even greater than in the Gaussian workload. As you can see, the Scylla can achieve about 180,000 operations per second versus 50,000 operations of Cassandra 4, which is about 3.5 times the difference. Scylla can handle 3.5 times more load of Cassandra. And again, we can see here that the Scylla latencies are pretty stable, all the way up to the 170,000 operations per second. The P99 latency remains under 10 milliseconds, and all the way up to 180,000 operations per second, the P90 remains under 5 milliseconds. While in the case of Cassandra 4, yes, it reaches 50,000 operations per second, but the latencies are pretty high at this point. As you can see, the P99 reaches 500 milliseconds and the P90 exceeds 100 milliseconds. So if you need, if your workload, if your use case requires you to maintain low latencies, then the maximum throughput difference becomes even greater. Let's say you need your P99 to be under 10 milliseconds. In that case, Cassandra 4 can only handle 30,000 operations per second, while Scylla can handle 170,000, which is nearly 6 times as much. Can we go to the next slide? So, in the 100% read workload, the throughput difference is much lower. Scylla only has about 2 times the maximum throughput of Cassandra 4. However, if you want your latencies to be really low, if your workload requires that, then the difference becomes a bit higher. For P99, if you require P99 latency to be under 5 milliseconds, then the Scylla can handle 40,000 operations per second with this requirement, while the Cassandra can only handle about 10,000 operations. So there is 4 times difference there, not the 2 times difference. Okay, let's move over to the memory intensive workload. And this workload is where the throughput difference gets really impressive. Scylla can steadily handle the traffic up to 200,000 operations per second, and all of it with P99 latency under 10 milliseconds. Cassandra, on the other hand, can't really handle more than 40,000 operations, which is 5 times less than Scylla. And this is memory intensive read-only test. And this is the test, I think, with the greatest throughput of all the free versus free tests. as Scylla can reach about, as you can see, 300,000 operations here. Although at the higher end, at the right end of the graph, the latencies of Scylla also go higher. The trend we have seen with Cassandra in all the previous slides. Nevertheless, if you need your latencies to be low, the throughput difference is amplified by that. So, for example, for P99 less than 10 milliseconds, Scylla can handle 240,000 operations per second, and Cassandra can handle 40,000 operations per second. So it's again the 6 times difference. If you are even stricter, can you go back a bit? If your requirements are even stricter, let's say you need your P99 to be under 5 milliseconds, then it becomes 180,000 operations versus 20,000 operations. So there is 9 times the difference. Yeah, so the Scylla, as you can see, is really great if you need consistent, stable, and low latencies with the high throughputs. Yeah, now we are again at the administrative operations part. As Piotr said before, those operations are really important and also should be benchmarked, especially adding nodes, as this is a very common operation. We need to perform it whenever your cluster isn't going to be able to handle the required load. So adding nodes faster means that you will be able to adapt your cluster to traffic faster, which in turn results in having a better service availability and lower costs, as you don't need to over-provision so much. As we have seen previously, Cassandra 4 is a bit faster in adding nodes than Cassandra 3. I don't remember the exact percentage, but we see that the improvement is there. However, even with this speed up, Scylla can double the cluster size, so add 3 new nodes, faster than Cassandra 4 can add a single new node to the cluster. I think the difference is pretty obvious. For the more precise numbers, let's see the next slide. So yeah, those are the times required to add a single node to the cluster. As we can see here, Scylla needs only 1/3 of Cassandra's 4 time to add a single new node with STCS strategy, and about 44% of Cassandra's 4 time when using LCS strategy. What's interesting to see, one interesting thing is that Cassandra 4 is faster with LCS than with STCS, while Cassandra 3 is visibly slower. So we can clearly see the effect of the newly introduced zero-copy streaming. But yeah, despite this new feature, Scylla is still much, much faster. Can you go to the next slide? So yeah, proportions of the bars are pretty similar here. The difference is just a little bit smaller. So to double the cluster size, Scylla needs about 44% of Cassandra's 4 time when using STCS strategy, and about 54% when using LCS strategy. Again, zero copy streaming helps. As we can see on the bars, it visibly helps, but it's not nearly enough to catch up to Scylla. Can you go next slide? Okay. So yeah, replacing a node, an operation which, as Piotr has mentioned before, should also be fast. As it is possible, you will be doing it when the node breaks, so you can be pretty much in a hurry, to maintain your service, to not let it go down. So you need to be able to replace node fast to be able to continuously handle load. Cassandra 4 needs about 25% less time to replace nodes than Cassandra 3 when using STCS strategy, and even more, 35% less when using LCS strategy. Even then, however, Scylla needs 75% less time than Cassandra 4 with STCS and 65% less with LCS. So yeah, Cassandra 4 is better than 3, but again, it's still got a long way to go if they want to catch up to Scylla performance. Okay, and yeah, this is the interesting slide, the major compaction time. The major compaction, as you can see, is where Scylla's sharded architecture can really shine. As you can see on the slide, the difference, I don't remember exact number, but I think it's about, Cassandra is about 50 times slower here. This is due to the fact that Scylla can perform major compaction on all its nodes, all its cores concurrently, while in Cassandra, the compaction is a single-threaded process. This results in a massive difference in compaction speed. Yeah, I think we didn't say that before, and it's a pretty important part of those benchmarks. But in those benchmarks, 3 versus 3 benchmarks, there was about 1 terabyte of data per node, if I remember correctly, and Scylla compacted it in 36 minutes. So yeah, it's about 40 times faster than Cassandra 3. Okay, now why are there 4 columns and not just 2 beside the Scylla column? After first tests, we are pretty surprised to see that Cassandra 4 had much worse results of major compaction than Cassandra 3. As you can see, yeah, the Cassandra 4 needed nearly 38 hours to perform this compaction, while the Cassandra 3 made it in a single day. Turns out it was caused, the cause of it was the change of the default value of one of the config parameters, namely the non-token parameters, as you can see in the description. Their previous default value was 256, and the default value in Cassandra 4 was changed to 16. And with this new default, the performance of major compaction is in fact much worse than in Cassandra 3, so it was not a fluke in our benchmarks. After switching this parameter to the old default value, performance of compaction is a bit better than in Cassandra 3. So yeah, I think it's really interesting that in Cassandra 4, this parameter has so much impact. As you can see in Cassandra 3, changing it to 16 manually doesn't affect the result that much. So yeah, there had to be some change in Cassandra code. So this parameter now really affects the major compaction time. Just to clarify, all the other benchmarks were performed with num tokens set to 256. So on, to 16, to the new default value. Only the major compaction we just tested. What caused this increase in the, what was the cause of the worse result?
Thank you, Karol.
Okay. Thank you.
Now we'll move to the other variant of the tests we performed. So up to this point, we have performed all the benchmarks apples to apples, running Scylla on the same types of instances, the same sizes of those instances, the same count of these instances to make those instances, those databases essentially run on the same hardware. In this test, we'll try to show that you can run Scylla on 4 nodes that are big nodes, which Cassandra 4 could have issue with running on such big nodes, versus Cassandra 4 running on a larger number of smaller nodes. So going back to the benchmarks setup slide, and focusing on the 4 versus 40 portion of this slide, we launched Scylla on 4 i3 metal instances. So those are their maximal instance sizes of i3 family. When it comes to Cassandra, we launched 40 instances of the same type as in the 3 versus 3 benchmarks. So there's a 10 times difference between the number of nodes, but the Scylla cluster nodes are much bigger. However, we also changed the loader nodes. We increased the count of them so that our benchmarks were not bottlenecked on the loader nodes. We probably did slightly over provision those loader nodes, but that means that we are safe in running those stress tests without worry. So first of all, this type of benchmarks is focusing on the fact that Scylla can run on smaller number of instances. Of course, they are bigger, but however, looking at the total cost of ownership, the total cost of ownership of Scylla when it comes to 1 year of ownership is $100,000 US, around this value. However, running those 40 Cassandra 4 nodes takes you $278,000. We chose the numbers of reserved instances, so the best numbers you can get on AWS, the lowest prices. So although the Scylla is running on less expensive hardware, both databases can achieve the same maximal throughput. Both databases could achieve 600,000 operations per second. However, Scylla, especially at those later parts of the graph, could achieve better latency numbers. All those latency numbers are below 10 milliseconds for 99 percentile latency. And for the 90 percentile latency, they are below 5 milliseconds. While we see that at the latter part of this graph, Cassandra is struggling. It's maybe becoming a bit overloaded by this increased throughput. So the last slide showed the write latencies. Here's the read latencies. They are a bit higher in both clusters, but the 90 percentile latency of Scylla is still below 10 milliseconds. And even the 99 percentile latency is below this value, this threshold, for a large portion of this graph. So summing up those two graphs, Scylla can achieve essentially the same throughput, a bit better latencies, especially at high utilization of this cluster. However, it's much less expensive compared to Cassandra. So another big advantage of running Scylla using 4 big instances compared to 40 smaller instances is that if you want to increase the capacity of the cluster, you don't have to add as many nodes as compared to Cassandra 4. So for example, if you have 40 Cassandra nodes, to increase the capacity of the cluster by 25%, you have to add 10 nodes to the cluster. And it might take, as you can see from these results, it takes about 16 times as much time to perform this operation. And what is worse, that you have to add those nodes sequentially. So adding the first node to Cassandra 4 cluster, the second node, third node, fourth node, the fifth node. And as you can see, even mentioning all those nodes is tiring. And it's also more tiring if you have to wait 17 hours and constantly monitor your cluster to check that those operations of bootstrapping nodes have completed successfully. While in Scylla case, you'll be done within 1.5 hours. So it's an easy operation to perform in a day. You don't have to prepare a big time slot to increase the capacity of the cluster. Now we look at the major compaction numbers. Here they are presented in terms of throughput. So in the previous major compaction slide, when it comes to 3 versus 3 nodes, so the same types of nodes, Scylla had an advantage because of its sharded architecture. So each core, each shard of Scylla database, in most cases it's pinned to each core or maybe each hyperthread. Each of those shards contains a distinct part of the dataset. This means that when you start a major compaction, each of those shards start a major compaction. And in case of Cassandra and Scylla, the result of major compaction is that every read will only come to a single SS table. So there's no difference between major compaction between Scylla and Cassandra. However, Scylla can utilize all cores because of its sharded architecture. So when it comes to 4 and 40 node clusters, we wanted to give Cassandra its best run at running compaction. So in this test, we run a major compaction on a single Scylla node, while in Cassandra's case, we run 10 concurrent compactions on 10 nodes, because there are 10 times more nodes in Cassandra case. So by doing this, we essentially increase the concurrency of the compaction process by 10 times in case of Cassandra. But as you can see from the graph, it's still nowhere near as fast when it compares to Scylla. And running those compactions concurrently is also a bit harder to do in Cassandra case. You need to start it on every node, when in Scylla you need to start it on only on a single node when it comes to this test that we performed. So now let's move to conclusions. So recapping all the results that we measured, Cassandra 4 has much better tail latencies than Cassandra 3, mostly due to the Java garbage collection improvements in Java 11 and Java 16. But still, Scylla performs 3 to 4 times better than Cassandra when it comes to those administrative operations, adding, replacing nodes. When Scylla really shines is adding capacity to this cluster that I showed a few slides ago. So increasing the capacity of this 4 and 40 node cluster is 11 times faster compared to Cassandra 4. Scylla major compaction is also much faster. That's due to the sharded architecture, and you don't have to manually shard Cassandra. Scylla has better throughput when you compare it apple to apple comparison on the same types of instances. But if we look at the P99 latencies, so if we want to have the P99 latency smaller, you might need to decrease the throughput of Cassandra 4, or maybe a bit over provision your Cassandra 4 cluster. And when doing this, Scylla has 3 to 8 times better throughput. And it's not only the performance differential between Scylla and Cassandra. Scylla is also less expensive to run. We've shown that it's 2.5 times less expensive compared to Cassandra in our 4 versus 40 nodes benchmark. So now a big question, should you upgrade to Scylla? Should you upgrade to Cassandra 4? So a few reasons that you might just jump into Scylla and consider it instead of moving to Cassandra 4. So first of all, upgrading is hard. You probably perform this operation many times. It might be very stressful to perform the upgrade operation. It could be problematic. So maybe before each upgrade, you want to make a backup. In case it doesn't really work out, you risk downtime. So it's still upgrading will be a bit harder whether you move to Scylla and whether you move to Cassandra 4. Of course, migrating from Cassandra to Scylla, we know it's a bit more involving. But first of all, the benefits we think are worth it. And moreover, we offer some tools such as the Spark Migrator tool that makes this migration process easier. And upgrading to Scylla will save you money in the long term. So as we shown in the total cost of ownership, when it comes to 1 year ownership of this cluster, it was hundreds of thousands of dollars difference. Scylla also has much better performance compared to Cassandra 4 and lower latencies that are not as easy to achieve compared to Scylla in Cassandra 4. And moreover, here at Scylla, we work hard at exciting new features that we introduce in each version of Scylla. So here are a few exciting new features that Scylla offers. So this year, we have introduced Scylla CDC. It's a change data capture technology, which allows you to track all the changes that are performed in a certain table. You can enable it on each table and track all the changes that are happening in this table in real time. We offer libraries for languages such as Java and Go for you to be able to consume those changes as they are happening in real time from your clients. We also offer the Kafka connector, which allows you to track all operations that happen in your Scylla table with CDC enabled and move those operations to Kafka and consume all the changes that happen in your Scylla database from Kafka. We also offer Kubernetes support with Scylla operator, which makes it easy to run Scylla using Kubernetes. And third of all, Scylla Cloud is a great solution if you want to reduce your maintenance time and have a managed solution that is easy to use and convenient. If you want to learn more about Scylla, you can visit Scylla University. Here's a link to it. And of course, Scylla is open source. You can download it and experience it yourself right now. So thank you for listening to the presentation. Now we'll read some questions and answer them.
Yeah, thank you, Piotr and Carol. It's time to hear from you, our audience. If you have any questions for Piotr and Carol, again, please use the Q&A button located at the bottom of your screen to ask your questions. Also, if you have any private questions that you'd like to ask, please use the Contact Us form on our website at ScyllaDB.com. We already have over a dozen questions asked during the presentation, so let's see what's already queued up.
Okay, so I can. So the first question is from Sarang. Is this DSX version of Cassandra? And no, I think this is the open source version. It is not the DataStax version of Cassandra.
Yes, we did use the open source version of Cassandra 4. We actually started working on those benchmarks even before the Cassandra 4 was released. Of course, those numbers are from the officially released version of Cassandra, but I don't think that the DataStax version was really available at the time we made those benchmarks.
Okay, so now the question from Dimitri. Did you try to use off-heap memtables in the tests of Cassandra? Piotr, could you
Yes. So I think I once tried to use it, the off-heap memtables. So first of all, I don't think it really improved the performance. And the second point is that I had some stability issues with off-heap memtables. Maybe it would require more fine-tuning. We did try to fine-tune the Cassandra configuration as much as we could to get the best results we could present for Cassandra. But for all the benchmarks that we have shown, we have not used the off-heap memtables functionality.
Okay, the next one we have is a question about the JVM. If Java 16 is not officially supported, is it not risky to use it with Cassandra 4.0 in production?
Okay, so maybe I can answer that. So yes, Java 16 is in fact not officially supported by Cassandra. We used it in our benchmarks because we wanted to get the best performance possible for Cassandra. But yeah, if you wanted to use Cassandra 4 in production, then this is something you should take into consideration, that your performance may not be the same as the performance in our benchmarks, because if you want to use JDK Java 11. In Java 11, from Java 11 to the Java 16, the ZGC garbage collector got quite a lot of improvements and functionality. So yeah, the latencies, for example, in Java 11 may be a bit worse than in Java 16.
Okay, let's see. The next question we have is from Andy, who's asking, performance of ScyllaDB looks so much better. What's the biggest concern I need to pay attention to if I want to use it to replace current Cassandra deployments?
Okay. So I'm thinking of all the possibilities that you might encounter.
Well, maybe talk about the shardware drivers. I think that that's a key differentiator, isn't it?
Yes. So for example, one thing that is different that we highly recommend when using ScyllaDB is to use our shard-aware drivers. So of course, Scylla is compatible with all existing Cassandra drivers. However, we have modified a select portion of them. So the Java driver, the Go driver, the C++ driver. We have modified them to take advantage of the sharded architecture of Scylla. So all the requests that are sent from our shardware drivers come into the correct shard at Scylla database.
All right, and let me clarify
That's
that for the
one
audience.
example.
Yeah, let me clarify that for the audience then. In the testing that we did you use the standard vanilla drivers for Cassandra, or did you use shardware drivers for Scylla?
So yes, we did use our own shardware drivers. However, when our shardware driver connects to Cassandra, it falls back to the old implementation, which we didn't modify, which is essentially the same
right.
as the non-shardware driver.
So they're backwards compatible. Okay, great, thank you. So we have another question here. With latency so low in milliseconds, seems like ScyllaDB takes away the need for building in-memory caches. Is that a right way to look at this?
So I think it depends on your workload, but for many workloads, it might be possible that you might not need to use an in-memory cache. And if you look at Scylla internals, we have our own cache that essentially performs as an in-memory cache within a NoSQL Scylla database. So it depends on your workload, but I think the best way would be to measure it. And even if after your benchmarking, if you see a need to use some cache, you are free to do it. It might be a good use case to combine Scylla and in-memory cache for certain workload types. So you might want to look at those graphs once again, and depending on your workload, so the disk-intensive workload, the memory-intensive workloads, those latencies are a bit different. So for some workloads, the latencies might be a bit too high to use Scylla as an in-memory cache.
Right, right. And by the way, if folks look at our website, there are some use cases where users were able to combine, let's say, a Cassandra and a Redis into a single Scylla cluster. So it really does depend upon your use case, but in many cases, you can get away with just the Scylla. Next question we have here from Adam Scott. In the benchmarks graph, the X scale shows 10 KS to 180 KS, but they are called operations by the presenter. Is it really operations and not just kilobytes per second?
Yeah,
yes,
those are definitely operations, not kilobytes per second, whereas operation is a single query. Like
and what was the payload size? About a kilobyte?
I think a bit less. It was for a single query. I think it was 300 bytes. Or
yes,
okay.
Yes, that's correct. We chose the default Cassandra stress payload size, which is around this 300 bytes.
Great. Right.
So you can read more details at the blog post. We posted the entire comments we used to read more about it.
Great. So yes, you can take those those are thousands of operations per second, multiply those by 300, and that's your byte count there. Ken asks, when adding a new node, can you remind us how much data is distributed across the nodes? E.g., surely it will take much longer to add a new node if there's 100 terabytes on each node compared to a single terabyte on each node.
Yes, that's something I should have mentioned at the beginning in the methodology section. But yeah, there was, I think, 3 terabytes distributed across the 3 nodes, so 1 terabyte on each node.
There you go. And that's in the 3v3. How about in the 4 versus 40? How much data was on each node then?
I think it was 40 terabyte data set. So for Scylla, it was 10 terabyte on each node, and for Cassandra, it was 1 terabyte on each node.
There you go. So then we have a question from Kuman. What actually happens when you add a new node or double cluster size? Why does Scylla need to do compaction when it adds new nodes?
So maybe I'll answer this question. So for example, if you have a 3-node cluster and you add at the 4th node, so when a new node is added, the database redistributes the data between the nodes. So there's when a streaming happens. Streaming is essentially copying the data from one node to another node. In case of adding a new node, the data is streamed from all the existing nodes to the new node. So about the compaction, yes, we mentioned compaction when it comes to those benchmarks, but we didn't mention them necessarily that the compaction is running while adding the nodes, although it might be running. We mentioned it because using the LCS compaction was supposed to give a bigger advantage to Cassandra 4, which has 0 copy streaming, which is supposed to work better with LCS strategy. So this compaction strategy doesn't really kick in when a new node is added. This compaction strategy would kick in when we first populated those nodes. So we added 1 terabyte to each node, and periodically the database would compact it to different SS tables, and the LCS SS tables are better for zero copy streaming for Cassandra.
Okay, great. Thank you. Dimitri's got a question. Did you compare your replace node test with the test published by Cassandra where they declared 5 times improvement? Why was the difference in results so large?
So we did it compare this particular version of the test, but of course there are many different avenues that those tests might differ. The schema might be different. During the replace node operation, in our test, there was a background load, which might have introduced some difference between those tests. And we also wanted to test quite a real case scenario. So I'm not really sure that the 5 times improvement is an average improvement.
Right. Okay, and then we have a question. What are the main reasons that make Scylla's performance much better than Cassandra's? So how would you answer that?
So maybe I'll take this question. So as you have seen, between Cassandra 3 and Scylla, and even Cassandra 4 and Scylla, the big differential between Cassandra 3 and 4 was the JVM algorithms that were used to garbage collect. Scylla is written in C++. We use our own framework C-star, which works close to the metal. We tuned it to work really close to the storage devices, to the network devices, while Cassandra has to deal with the JVM, with the garbage collection mechanism. So the first part of the difference is the language difference. Java has to have a runtime. However, as you have seen that Java is getting better and better, especially with new garbage collections mechanisms. And the second part is that we really hard-tuned the C++ code to be as fast as possible, to have a sharded architecture. So for example, in our sharded architecture, each core is a separate process that doesn't share that much data between all other cores. So if you have a CPU that has many cores, it might be possible that you have many NUMA nodes, and moving data between those NUMA nodes can be quite expensive. And from the first days of Scylla, we really optimized the database to not share many data between the shards, and that's why we recommend the shard-aware drivers. So the drivers we have modified to take advantage of.
Great. Thanks for that answer. I think some of the newer JVMs are starting to become NUMA aware, but I still think that that's still early for them. So maybe you'll see more performance improvements over time with JVMs. Let's see.
This GC garbage collector we use. I think in its description, I saw that it claims to be NUMA aware.
Right.
I'm not sure what it means with the garbage collector, but yeah.
Exactly. Okay, let's see. In the comparison of the 4 versus 40, why was Cassandra tested on 4x large and Scylla on, those had 16 vCPUs and Scylla at 72 vCPUs? Is there a limit on the number of vCPUs that Cassandra can have on a node?
So maybe I'll answer this question. Although we didn't test Cassandra running on its own on this large mental instance, we know that the Cassandra developers and also DataStax recommends that you run multiple instances of Cassandra on each node if you have a very big node. However, running multiple instances of Cassandra can be quite tricky to set up, and it really increases the numbers of configuration, maintenance that you have to perform. So we didn't want to present Cassandra with bad lights at some worse conditions that are recommended. That's why we chose to use smaller nodes. And I also think that many commercial deployments across the industry really confirm this point that many large companies use very high node count Cassandra clusters, maybe hundreds of nodes. Maybe I think the top value was like in thousands of nodes, while our users really prefer to use larger nodes, and that's what we recommend for our users.
Right. And speaking about commerciality, Dimitri was asking, does the cost comparison for 4 versus 40 include ScyllaDB licenses, or did you use the open source version there too?
In both cases, we use the open source version. The cost includes only the servers, the AWS servers. So on the Scylla side, it's the Scylla Open Source version, and on Cassandra side, it's the normal vanilla Cassandra, not the DataStax version.
Okay, we have a question from Andy here. Does ScyllaDB support user-defined functions? How does it perform if you happen to have if we have any performance metrics on UDFs?
So I really can't talk about. I don't have much knowledge about performance metrics. So with user-defined functions, this functionality is currently an experimental feature. Of course, you can easily turn it on by providing a correct flag to the configuration of ScyllaDB. However, it's still an experimental feature. A difference between UDFs in Cassandra and in Scylla is that in Scylla we currently support Lua UDFs, while Cassandra I think also supports Java and JavaScript, if I'm not mistaken. However, maybe I'm not sure about the availability of this this solution, but we are working on the WebAssembly user-defined functions in Scylla. I think the very initial version was released, was committed to the master. Of course, it's still experimental. When it comes to WebAssembly, it's very initial implementation, very much experimental. But as you can see, we are improving Scylla also in this case.
Great, thank you so much. And so let's see, somebody was asking, can you go back and just tell them what the repair times between Scylla, Cassandra 3 and 4 were? So I don't think they believe the numbers the first time you presented them. So you could just go over the repair times then?
I don't think we have presented repair times.
Oh, okay.
Yes, we have the replace node operation. However, we did not test the repairing of the nodes operation.
All right, so maybe that's something
it's a bit different from replacing the node.
Yeah, but in the I believe in the blogs we have the test set up. So if somebody wanted to do their own repair time test, you could just reproduce what we had and run your own test. And I'd love to hear the answer if you do that test run. Let's see. The next question is Rajesh. In the comparison of 4 versus 4. Oh, no. Let's see. The next one here. Second question. What level of DBA knowledge is needed to tune and maintain Scylla to achieve these levels of performance? Or put another way, what level of tuning was done on Scylla to achieve these numbers? And did you have to do a similar tuning effort and skill to tune Cassandra 4.0?
So I can answer that from the perspective of someone who is not that much experienced with the Scylla and Cassandra and the whole, high performance NoSQL world, as I am pretty new here. So during the benchmarks, I think a lot more time went into actually tuning Cassandra, making sure it runs at the top of its game. In Scylla, in the Cassandra config, there are many values that you can change, and each of those values can have an impact on the performance. Apart from that, you also need to tune the JVM, the garbage collection. So yeah, there are a lot of places in Cassandra that you need to tune so that the performance is optimal. In case of Scylla, the configuration is pretty simple. I feel that it is much simpler than Cassandra. Also, the Scylla has the IOTune program that benchmarks your disk, outputs the file with the optimal parameters for your machine. And that's pretty much the performance configuration here.
So maybe if I could add something to this answer. In our tests, we of course run them on AWS. So we used AMI images that are officially supported and released by Scylla. And what's great about those images that we have already measured the performance of different AWS nodes. So if you start an AMI instance, it will check the instance type and preload correct configuration for this node type. So essentially, you'll just start it up and it's tuned from the box, out of the box. And in case of Cassandra, we spent a lot of time to tune it. We tried to stick to all best practices. Of course, we at Scylla have, this is not the first time we have measured Cassandra and benchmarked it. So we have built on the previous knowledge of other people in the company and also people outside of the company that have experience with Cassandra. We really wanted to give a fair benchmark results of Cassandra to really see the best performance it could achieve.
Great, thanks guys. Hey, listen, next question is, was the TCO comparison done with Scylla Enterprise at all?
So I haven't made this calculation. However, it's very easy for you to perform this calculation by yourself. We have a calculator that measures that you can type in the instant types. You can select the load. So for example, how much data you have in the database, and this calculator will show you the cost of it running
Exactly.
at cloud, and it includes the enterprise versions and all the metrics. Unfortunately, we don't have the final results ready for you just right now, but I think it's very easy to just go to the calculator and that we have our own website and calculate it on your own.
Yeah, and just to clarify for listeners, that is the Scylla Cloud calculator. Remember, the Scylla Cloud is a fully managed database. So we're going to be doing all the backend administration there. So if the price is more than, just vanilla Scylla Enterprise, that's because, again, you're getting all the backups, restores, upgrades, all that's being managed for you, all the DevOps side of things. And then the other thing I want to mention about TCO comparison is that remember that Scylla Enterprise also has a feature called incremental compaction. So you're actually going to be saving on the amount of nodes that you need to store data, right? You're going to get better utilization out of each node in terms of how much data you can keep in those systems. So you might actually have a skinnier cluster with Scylla Enterprise compared to Scylla Open Source. All right, let's see. Another question here is, do you guys have any idea how many major contributors do we have for Scylla Open Source outside of the ScyllaDB staff?
So I'm not quite sure about the numbers, so I don't want to overestimate or underestimate it, but I think I heard Avi Kiviti, our CTO, saying that that the number was unfortunately not that high, but we had a few contributors.
Yes, yeah, we don't have many, but what's interesting is that like one of our open source contributors contributed the entire Redis API as an example of what you can do on top of Scylla's framework. So yes, we might not have many open source contributors, but it is amazing what we see from our open source contributors. I also want to give a shout out to Ultrabug, who was one of the major contributors that got our, it's not just the core server, but he helped get the Shardware driver for Python going. So again, there's different ways to contribute to our open source community.
Yes, and I saw a contribution that I think will be merged quite soon to the Java driver regarding the advanced shard awareness functionality, which is also coded by the member of the community.
Yeah, and in fact, I also believe our Scylla operator came from Yanis Zakardis, who, so he wrote an initial Kubernetes operator for us, and that's now available from us, and we've taken it on from him. But so it is, I think it's actually amazing to see some of the key contributions. And, maybe not the largest number of contributors in the world, but we are small but mighty. Let's see, next question here. Can you give advice about deploying in a cloud environment? All of our I/O OpenStack is currently shared, and we live with the risk that the shared I/O could die all at once. This has happened. So presumably your cloud environment allows deployment of local storage associated with the node. So yeah, maybe you want to talk about RAID 0.
So when I think that the default, so by default, I think the AMI images on AWS start, they create a RAID of all NVMe disks that are in this machine and create a single large pool of storage. We use RAID for that, but I think that it can be changed to give you better security.
Yeah, so again, I think most of the kind of instances we recommend would be like the i3 or i3EN, which have their own native storage as opposed to using some sort of network attached storage or some sort of, ephemeral storage. So that would be my my understanding. But again, if you have some sort of like policy things where you need to use some sort of disjointed layer from your compute and your storage, then that's something you probably want to talk to our solutions architects. And I'd recommend that you just use the contact us form, tell us more about your use case, and we'd love to talk through what your issues are. Does that make sense? All right, so those are the questions we have. I wanted to thank Piotr. I want to thank Carol. You guys did a fantastic job on this. You know, just the number of questions shows that we have a wonderfully engaged community here. I wish to, you know, again, follow up with us if you have any additional questions. But for that, on behalf of all of us here at ScyllaDB, we wish you a great evening or day. Bye-bye.
Thank you. Bye.
Bye. Thank you.